We're in the middle of a slide. We'll come back to that slide in a sec. As usual, I want to start with a problem whenever we can. We'll do the come-up roll. Okay, so slide 20, the come-up roll, talks about the game of craps. In the game of craps, initially you have what's known as the come-up roll. Okay, so the shooter will roll a pair of dice and take the total. If the total is 7 or 11, it's a natural win. And those two things are much more likely than craps, which is if it's a 2, 3, or 12, it's craps, and it's an instant loss. Other things will change the game. So a 4, 5, 6, 8, 9, or 10 is known as a point. And once you roll one of those, say you roll a 5, the objective of the shooter is to roll another 5 before they roll a 7. Okay, so it's not a come-out roll anymore. So none of these other objectives matter. It's all about rolling a 5 before rolling a 7, which is not as likely. Okay, so there are 5 ways of rolling a 5. And then, of course, there are 7 ways of rolling a 7. And you'll probably analyze a problem like this at some point where you keep on, tossing coins or tossing dice until one or the other thing occurs. Any other outcome you re-roll. This is not an infinite process, although I guess technically it could be. It never is in practice, and your chances of winning are, well, it's basically 4 out of 10, because there's 4 winning conditions and 6 losing conditions. Okay, so spoil the punchline a little bit for you. That's what it ends up being. Anyway, you're going to verify one of these eventually on an assignment. Perhaps it's a fun game. It's one of my favorite games in a casino, and the spirit is infectious once the roller gets going. If they're on a winning streak, it's a lot of fun. There's a lot of camaraderie at the table, and it's a fun game. It's a little bit better than blackjack, which is a little bit depressing. But anyway, I digress. We have a bunch of rules about probability now. A lot of them deal with things that look like set theory, but they are probabilistic in nature. Okay, question 1 is, what's the probability of a natural win? We're going to call this event A. Okay, so A has 2 things in it. It's either 7 or 11. Okay, so, whichever way you want to look at this, you can look up the individual probabilities and add them up. I mean, maybe that's the best way to do it, as a sum. We know the individual probabilities because, well, we can count them. The probability of a 7, of course, there's 6 possibilities out of 36 in the sample space. Everything is equal. Probability of 11 is 2 out of 36, right? It's either a 5, 6 or a 6, 5. Okay, so you can add these things up, each individual probability in the function. Maybe I'll change color here just to make it a little nicer for you. Okay, so the probability of A is the probability of each individual outcome added together as a sum, okay, which would get us 636 with 236. I'm not going to write that step out. We'll just add those 2 things up and take it the lowest terms. It's 2 by 9. Okay, probability of craps, we'll call this event B. And again, same thing. I don't want to spend a lot of time on this, so maybe just writing a concluding statement's good enough. Chances of 2 is 1 in 36, 12 is 1 in 36, 3 is 2 in 36. So the probability of B is the sum of those things. The probability of 2 plus the probability of 3 plus the probability of 12, and that's 4 by 36, or 1/9. Okay, these are pretty easy, and they follow from just the definition of probability function. Okay, part C is interesting, more interesting anyway. Okay, because it's actually going to use some of the axioms that we have seen. Okay, so what's the probability of some other roll? So in terms of A and B, what is the thing that we're going to find the probability of in terms of A and B? Good, sort of. I mean, definitely A or B is going to be in there. Okay, so A union B. I don't think you have the knots in the right places. Okay, so you suggested that we put a knot over each of the A and the B. Right, not A and not B. Okay, so you just have to be very careful that if you're going to expand it, you use De Morgan's law correctly, right? So yeah, you corrected yourself, you changed it to intersect. Okay, so we'll start with this, all right? So it is everything that is, well, in A union B, we don't want that. Okay, so some other roll is either A or B, but not that. And we can simplify that thing out, not by using De Morgan's law, but by using which rule? Yep, not the difference rule. Complement rule. What should I write? You don't know. Somebody help him. Good. Okay, and we can go further. What can we do to a probability of A union B? What can we do to probability of A union B? Okay, so what should we write? Good. Okay, so the rule of sum, that was an axiom. Okay, so we can feed A back and B back into this and get a result using two of the rules that we developed last time. So this is 1 minus 2/9 plus 1/9. So 1 minus 3/9 is 6/9 or 2/3. Okay, good? Good. All right. What's the plan today? I wanted to finish packet 3 today, but I know there's not enough time. And I want to talk to you about the birthday paradox because your assignment requires it. Okay, so I'm going to jump around a little bit just to make sure that we get the analysis done. There are about 4 computer sciencey applications of that material, and I will cover that because it's really important, but it's not important, it's not critical for your assignment work that's due Friday. Okay, so we'll leave that until Wednesday. Okay, so that's our plan today. First we need to go finish this monotonicity thing, and then we'll get to the birthday thing. All right, so this is the last of the probability rules derived from set theory and the Kolmogorov axioms. And just to refresh you, get us back in the same on the same page as it were. If A is a subset of B, what can you say about the relationship between their probabilities? And indeed, if A is a subset of B, they should follow a less than or equal to thing. We looked at the strictness thing yesterday, and it feels like it should be strict inequality, but it might not be if the probability of the things that are different equals 0. We don't have a lot of cases where probabilities of outcomes equal 0. They're not very interesting, but in a strict mathematical sense, this can happen. Anyway, this is where we left off, and our next goal is to prove the theorem. Okay, so what do we know? Well, we know some things already. We know the difference rule. Okay, so the difference rule. The difference rule states that you get the probability of B minus A equals the probability of B minus their intersect. Okay, their intersect is kind of interesting because A intersects B, it intersects at exactly where A is. Okay. And this is an interesting consequence of A as a subset of B. You can actually get 2 equation-like things that come out of this. So if you imagine you intersected A with B, you should get everything that's in A. Everything in A survives. Okay, so that's one thing. It's an if and only if relationship. So if you have A intersect B equals A, you get that A is a subset of B, and vice versa. And you can also get something for A union B. What would A union B be equal to if A is a subset of B? B, yeah. So everything, you're not adding anything to B, to the elements of B, because everything in A is also in B. Okay, so these 2 things are an if and only if relationship. So because you have A as a subset of B, you get these things. This is the one that we care about, and if we apply the difference rule, as you'll see, it will drop right out. Okay, so let's just write a bit about that. So since A is a subset of B, then A intersect B equals A. And using the difference rule, the probability of B minus A is equal to the probability of B minus the probability of A intersect B. Okay, but this equals this, right? So we can plug that in there, and we end up getting the probability of B minus the probability of A. Okay, well that's kind of cool. The probability of B minus A equals the probability of B minus the probability of A. And maybe that's a cool thing to have proven, but that's not the thing we're after. Okay, we want to show the probability of A is less than or equal to the probability of B. And we just need to relate them, I guess, by subtraction. That's basically what's happening here. If you imagine tossing probability of A onto the other side, you get probability of B minus probability of A is greater than or equal to 0. Okay, so we can just do that in a clever way. I guess we can turn this thing around and put the probability of A on the other side just to make it look like the thing we want. I've run out of room here, so maybe I'll just do this sort of thing. Okay, so this means the probability of A, if we put it on the other side, is equal to the probability of B minus the probability of B minus A. Okay, but this bit here is less than or equal to the probability of B. Now, why is that? Why can I say that? Oh dear. Yeah, this thing can't be negative, right? Okay, so we're actually subtracting off either 0, in which case it's equal, or we're subtracting off something that's positive, in which case this has got to be less than this. Okay, so you can imagine that we're actually approximating this thing by 0. Okay, and these things it's ends up getting sort of stroked away as a result. Okay, and so you're subtracting a non-negative number. You can approximate it away. I think we saw this when we did the union bound. Okay, so that's it. Okay, so quick and easy proof, and an application of this. Okay, so we'll finish off the lottery example. You buy 3 lottery tickets out of a pool of 1,000, 10 winning tickets. What's the probability the first ticket you buy is the only one that wins? Okay, so we had this thing defined before as A is the event the first ticket wins, B is the event the second ticket wins, C is the event the third ticket wins. Okay, I don't want to write that out again, but we'll just say let A, B, and C be as they were before. And the event that we're seeking is that the probability of the first ticket you buy, so A is the one that wins, and B doesn't win, so B bar, and C doesn't win, so C bar. Okay, so the intersection of A with B bar and C bar. Okay, and you can calculate this thing out exactly. You can take them as permutations and say there's 10 possibilities for the first thing and 990 and 989 and then divide it by 1,000 times 999 and 998. You can do that. You can come up with an exact number. Okay, I want to use this. Okay, I want to use what we just did, monotonicity, to get some sort of estimation, to upper bound what the probability is. What's the probability that the first ticket wins? Well, it's 1 in 1,000. Okay, what's the probability that it's the only ticket that wins? Well, it's less than 1 in 1,000, or sorry, 10 in 1,000, 1 in 100. Okay, so how much less? I don't know, but I know that it's definitely less. Why? Well, this is a much stronger event, right? So it must be a subset of the probability of A. Okay, so we're going to use the probability of A as an upper bound for this. Okay, so we know that A intersect B intersect C, sorry, B bar intersect C bar is a subset of A. Okay, why? Well, there's more restrictions over here. It's got to be. Right? And the probability of A is 1 in 100. So, by monotonicity, the probability of A intersect B bar intersect C bar must be less than or equal to 1 over 100. Okay, and if you think that's kind of crude, maybe it is. But the actual answer, okay, if you calculated it out, it's 0.00982. Okay, so it's actually not very far off. Okay, so this gives us an upper bound, and sometimes an upper bound that's close is good. Cool. Yeah. Say that again. Can you solve it like this? Yeah, I mean, if I ask you for an exact answer, probably you need to do the exact thing. And if I ask you for an upper bound that's reasonable, then you can do this. Okay. All depends on the context of the question, of course. Cool. Okay, other questions? All right. Summary slide. And I don't know if you like these summary slides. I sort of like them. You get all the formulas and stuff in all the same locations. A couple of these things every single packet, which is nice. Okay, these are all of the rules that we derived. Okay, and the axiom, main axiom in there. Anyway, so we have for any events A, B, the difference rule. So probability of B minus A gives us the probability of B minus their intersect. Probability of intersect. Okay, so that's a good rule. We have the inclusion-exclusion rule, which sort of falls out of set theory. We just put probability things around it instead of absolute value things. You get to use this on your second assignment to prove the inclusion-exclusion rule for 3 sets, 3 events. It also works. If A and B are mutually exclusive, they don't overlap, then you get the axiom. Okay, so their probabilities add. Okay, so it's sort of like the inclusion-exclusion rule for this probability being 0. Okay, so it's a sort of application of that, but not really. This was derived from this. But definitely, if they have a non-zero overlap, then we end up getting an inequality. Okay, so this works for 2 sets, and it also works for a countably infinite number of sets that don't overlap. They're mutually exclusive, or you just get a union bound for however many sets you want. And then you can use complement. Okay, you can count the things or take a probability of the things that you don't want and subtract it from 1. And we have an inequality for subset as well, which we just did, monotonicity. Okay, so any questions about this before we get to the birthday paradox? Yeah? Yeah, all right, let's do it. Okay, we have 25 of you. Oh, nice, okay, 25 of you chosen at random. What are the chances that at least 2 of you have the same birthday? And I made it multiple choice. Okay, so either it's 1, it's not very likely, less than 20%. 2, it's around even chances, around 50-50, so somewhere between 30 and 60%. Or 3, it's very likely, something 70% or above. As usual, with these multiple choice things, I like to have you vote, so you get a chance to hone your mathematical intuition, and this will be no different, and ask you to make your choice. Prepare to vote. Okay, ready? Everyone made their decision? Yeah? Okay, let's vote. Who thinks it's 1? Not very likely. Less 20% or less. Hands nice and high, please. Count them. Thinks it's 2, between 30% and 60%. Hands nice and high, please. And who thinks it's 3, 70% or more, it's very likely. Okay. Now let's see. What we got today? 1, 2, 4, 5, 9, 15, 21. Uh-oh. There are 27 of you in this group. 2 of you are going to be left out. You're smiling. You don't, yeah, you want to be left out. That's cool. All right, so let's make sure I got the count right. 1, 2, 3, I got 5, 10, 11, 17, 21, 25. You're left out. Okay, so the target group is you all in this section, except you and you. Sorry. None of you. None of you. None of you. Okay, so 25. Did I count it right? Somebody double checked, right? Must be 20. Okay, 25. Okay, let's do it. Okay, January. How many of you are January? Yep. 14th? 5th. February. 29th? 24? 21. Okay, March. Sorry, no luck for you. April. No April? Wow, that's cool. May. All right, start with you. 24th? 16th, 5th? 6th? Did I hear another 6th? No. 4, 5, and 6. Oh, all right. June. Okay, June.
26th.
July.
7th.
4th. July 4th. Fireworks. August. Oh, sorry. You're only the one. Okay, you revealed that information. Okay, sorry. All right. September. Oh, October. Okay, November.
26th.
And December. Oh, fail. You know, I do this in Mecca 101, which I've taught a long time, a lot of years. And but I do 30 students instead of 25. And until last year, it had never failed. There was always at least one pair. And last year it failed. And you guys are the second fail case of all time. This is only 25, but the 30 is 70 or more. The 30 is about 70%. So I guess I'm due for some failures. Well, yep. 5 more people at random and see if they match? Okay, you want to do that? I mean, we could see. All right, who looks random? All right. You 5 look random. All right, how about you?
July 7th.
July 7th? No. February 27th. I don't think that was one.
April 26th.
Okay.
May 16th.
Oh, we got one there. May 16th and November 8th.
Wait, did you say July 7th? Yeah, that's 8th.
Okay, there we go. 2 pairs now. So we just needed more people. All right. Good job. Yeah, so it's actually around 50%, and we're going to analyze it now. Okay, and it seems like it should be not very likely. I remember the first time I heard about this demo, I was in high school, and one of my friends told me about it, and it felt like they were cheating. The teacher was cheating because there were twins in the class, and it's just like, it's too bad. Okay, so first thing is we have to model this as a sample space and a event space, right? And this requires some assumptions which might not be true, okay, in real life. Okay, so first of all, there are 365 possible birth dates. Yeah, of course, we know that there are 366 possible birth dates, right? It's February 29th. Every once in a while I get a student who was born on February 29th. It happens pretty rarely. Is anyone in the room born on February 29th? Yeah, it's kind of interesting what happens. And every government treats February 29th a little bit differently. I play bridge. I met lots of old people play bridge, right? But I met somebody who was born on February 29th. And it was her birthday. I was there for her birthday. She says, I turned 18 today. I'm like, really, you turned 18? Of course you turned 72, right? Anyway, anyone know what they do? Like what the Canadian government does for people born on February 29th? But their legal birthday is actually like March 1st. Anyway, it's an exception that's handled differently for country by country. But anyway, we assume that everyone's 365 choices, each equally likely, which is also not true. If you look at the distribution of birth dates, the most likely month is September. Yeah, why September? Yeah. Christmas and New Year's is a time for celebration. Yeah. Okay, so if each of you were to sign a calendar or to write down your birthdays as a sequence, okay, there'd be 365 different possibilities. So you can imagine it's like an ordered an ordered n tuple with 365 different possible characters. The students that we chose in an order, they generate a sequence in 365 to the 25 ways. Okay, so that's the number of possible sequences. We're actually trying to find the ones where you're guaranteed to have at least two of the same. And this could come in like a pair or a triple or two pairs or a whole bunch of different things. And you sort of saw on your assignment, you have your password problem, right? Rather than take all those cases, you can just count backwards, right? And go for unique birth dates and then subtract it off the total. Okay, so counting backwards, if we let A be the event that at least two students we should note that it's easier, actually it's way easier, to compute the size of A complement, the event all birth dates are different. Right? Because the size of A bar, what is the size of A bar? Did you put up your hand? No. Good, yeah. So it's a permutation of 25 of 365 objects. You've made the factorial out of that. That was nice. Okay. And by counting backwards, we can use the complement rule. And you're right. Okay, so you're right the way that you stated it, right? It's 365 factorial divided by 340 factorial, which ends up, getting us a whole bunch of numbers. Okay, and we wouldn't want to put this in our calculator; it would catch fire. So what we would do, and again, this is the same trick I keep mentioning. If you wanted to compute this thing, okay, so you'd write out the numerator as a product. The denominator is also got 25 terms in it. And then you would multiply by these fractions that are close to 1 and expand them out. Okay, and this would make sure that the numbers don't overflow. And if you do this, you get around 57%. Okay, there was a hand that went up while we were doing this. Sorry, why is it what? Why is it ordered and not a selection? I don't know. I don't know that it's easy to do a selection, right? Like if everyone has unique birthdays, then sure. But if you have duplicate birthdays, a selection, I don't know how you would do it actually. Well, I'm selecting 25 students, but their birth dates are the things that we're arranging, not the students. So, so if it was me selecting 25 of you, it would be like 180 choose 25. But it's actually the birth dates that we care about per meeting. Yeah. So maybe that's the source of confusion. Okay, good. All right. So, okay, sorry, I'll leave that up a little bit. Okay, so we'll skip to number 27 so that we generalize this. Okay, so this is a problem that you've explored on your assignment, maybe. Okay, so there was the function counting question. We did a couple function counting questions earlier on, and this generalizes to how many ways can you put n balls into d bins so that no bin has more than one ball in it. Okay, so how many injective functions can you get, or what's the probability you get an injective function if you pick a random function? Okay, so you have n pigeons and d pigeonholes, and you put them in randomly. What's the probability that you don't have two pigeons in the same hole? Okay, so we're going to generalize this thing using the same technique. Okay, but instead of 365, we have d days. Okay, instead of 25, we have n. Okay, so let's do that. Okay, so let S be as before, where we take our n students, and each of them has a birthday, one of d possible things. We're basically making a function out of y'all. And let E be the functions that aren't injective. Okay, that you end up getting two people with the same birthday. Okay, as usual, we count backwards, and the size of E, well, we can make an injective function by saying, okay, there's d possibilities for the first thing to be mapped to, and there's d minus 1 for the next one, and d minus 2, and so on, all the way down to d minus n plus 1. Okay, and then we do the exact same thing. Take the probability of E as a 1 minus the probability of E bar, and it's 1 minus d times d minus 1 times d minus 2 times d minus n plus 1. And this is divided by d to the n, but there's there are n terms on the top and factors on the top, there are going to be n on the bottom. I'll give you a moment to catch up. Okay, so these are individual fractions. Okay, and if we were to look at them sort of holistically, that one is 1, d over d is 1. This is, 1 minus 1 over d, right? It's just a little bit less than 1. This is slightly lesser than that, 1 minus 2 over d. This is 1 minus n minus 1 over d. Okay, so they all sort of fit that pattern. Okay, so this is equal to 1 minus, just to complete the pattern, 1 minus 0 over d times 1 minus 1 over d times 1 minus 2 over d times 1 minus n minus 1 over d. Okay, so hopefully you're okay with that step. Nothing really happened there, except we have a whole bunch of things that are kind of close to 1. And there's a very useful, A, a very useful rule, and B, a very useful approximation, and they're shown in the boxes at the bottom of the slide. So I'm just going to get the boxes up here. Okay, so one useful bound is that 1 plus x is less than or equal to e to the x. Okay, there's going to be a lot of e coming into our discussion coming up. Okay, and I've shown the plot here, and you can prove this using calculus. There's a whole bunch of different proofs out there. I'm not interested in proving it, but you can bound anything that looks like this. It doesn't matter if it's 1 plus x or 1 minus x, whatever. It works faithfully. And it turns out that this is a really, really good approximation if you're close to 0. So 1 plus x you can rewrite as e to the x, basically, if x is very close to 0. And I don't know if I was in my right mind when I plotted this, because this is a blow-up of basically this area right in here. And, the difference in there, like, it's very slight. Like, the blue line is basically hugging the red line. It's off by, like, 0.5% on the high end or the low end. Okay, so you don't get very much, it's curved, but it's not curved by much. You're right, sorry, this should be minus 0.1. That should be plus 0.1. Okay, thank you. Anyway, we are going to approximate each of these things by an e to the something. Okay, so each of these, we're going to use this one down here. It's less than or, each of these is less than or equal to, so because it's negative, this will be greater than or equal to 1 minus e to the minus 0 over d times e to the minus 1 over d times e to the minus 2 over d, and so on. This would be e to the minus n minus 1 over d. And this is you can use the exponent rules on this. You end up adding the powers together, and when you add up the powers, well, maybe we can just rewrite it as sure, why don't I just write it down as a step here. This is equal to e to the sum from I equals 0 to n minus 1 of minus I over d. But it's basically like, 0 plus 1 plus 2 plus all the way up to n minus 1. And we know that. That's a familiar summation, right? It's n times n plus 1 over 2, except it goes all the way up to n minus 1. So it's actually going to be n minus 1 times n over 2. And of course we have the d in the denominator. Okay, so this is an approximation. It's not an exact thing. But I did this, I made this plot of, sorry, that's not the right one. I made this plot, okay, of the birthday thing for, the actual thing, like if you run the thing through a calculator. And it follows it pretty closely. So the approximated p is the red line underneath here, and the true p are the blue dots. And it's just a hair below. Okay, so it's just a hair below in each case. What we did in class was, initially it was 25. So it's this one here at 57%. Even money would be here at 23. Okay, and can we get that out of this? Well, yeah, we can. So if we wanted something like, say, we wanted 50%, this n times n minus 1, we could approximate that as n squared. We would like that value to be the natural log of 2, because that will get us a half out of this thing. Okay, so to get natural log of 2, so we would want n squared over 2d to be equal to the natural log of 2. We would solve for n. Okay, so how many trials do we have to get? We get that n is equal to 2 natural log of 2 times d, so it's 2d, and square root of that. And if we pump in d is equal to 365, we get 23. Okay, so this is the generalization of, instead of birthdays and people, it's just functions. Okay, this has a lot to do with like how hash tables work and so on. We'll talk a bit about what the applications of this thing are. Okay, but anyway, are there questions about this? Okay, this is the likelihood that you're going to get at least one pair. Okay, it's a break even at 23. And you can find the break even for anyone. I want to show you a second problem. It's a related problem. Okay, so I'll show you a related problem. And this is a different birthday variation. Okay, so suppose we selected n of your classmates at random. What's the chances that they match your birthday? Okay, so this is different than, taking 25 of you, we find any pair. No. You have a birthday. I mean, I have a birthday. You didn't mention my birthday. What are the chances that, how many people do I have to look at before I trip over somebody that has my birthday, matches my birthday? Okay, this is a slightly different problem, but we can do something similar with it. Okay, so solution. As before, assume 365 to the n possible sequences. And we're looking for, likely. Okay, so I mentioned before, the probability of this thing happening is around a half. Around a half is sort of likely, and this is where we get a power of natural log of 2 in the exponent. Anyway, if E is the event, at least one matches your birthday. Then E bar is the event that everyone misses your birthday. Okay, and it doesn't have to be unique birthdays anymore. Just they could be the same birthday n times in a row. Okay, so instead of getting a permutation, you actually get 364 to the n. Everyone misses your birthday, and we use the complement rule again. And so the probability of E is 1 minus the probability of E bar, which is really 1 minus 364 over 365 to the n. Now, as these numbers get tinier and tinier and your n gets larger and larger, your calculator starts to also have problems. The closer you get to 1, because your decimal tail ends up being a bunch of zeros. So what do? You use calculus on this. Okay, so you can rewrite this thing in the same way that we wrote the previous one. It's something very close to 1. And we could use the same approximation. We end up getting the same result is what I'm going to show you here. But this is a thing from calculus where this is the definition of E. Right? So if you have the limit as n tends to infinity, it's like the compound interest formula. So you have a diminishing compound interest, but you take it for so many years. And the more, the smaller your interest is, the more years you do. It ends up converging to E. Okay? This is very close to this. If we were trying to make this thing look like this, what I would do is I would try to make this look like this. Or you could just do like e to the minus 1, 1 over 365, and then exponentiate that to n.